reward is based on the intersection over union. For instance, when you zoom into a region where the object is present, the intersection over union of the current state would be much larger than the previous state. Therefore, positive reward. And if it's not the case, then the agent would receive a negative reward. Similarly, for negative reward, for upscaling, we always give a negative reward for upscaling as it might be expensive for us to process these larger resolution images. But for later stages, we give less negative rewards as the size is smaller. Therefore, the reward is based on the size or the resolution that the model is working on. For terminal action, we give a big positive or negative reward depending on the IOU threshold. Did the agent terminate at a responsible bounding box or a reasonable bounding box? If yes, then a large positive reward. If not, then a large negative reward. Now let's look at an illustration of how the method works. Starting from the original image, the agent has 7 different actions to choose from: to increase the resolution, to zoom into top left, zoom into top right, bottom left, bottom right, center, or terminate. In this particular instance, the model chose to zoom into the top left. Then we manually crop into that region and then feed that as a new state for the agent to look for. The process continues. Now let's look at the model architecture. CED-QN uses a contextual network for feature extraction and a Q network for approximating the Q values. We do not train the contextual network as it comes pre-trained, so we freeze that network. The Q network consists of 2 linear layers with ReLU activations. The model architecture is designed to be lighter compared to previous works. Now, for training, we found that previous methods use Q learning and it is unstable and seem to be steered by maximization bias. One issue with deep Q networks and Q learning algorithms is the tendency to overestimate the Q values. This could be seen in the training of our agent, where the agent always asks for a higher resolution image. Therefore, we propose using double DQN, where we maintain a copy of the original network, the target network, and update it less frequently than the main network. This way, we can avoid any bias from the main network as the target network pulls the bias back. CDQN uses a replay buffer and exploration to improve learning efficiency. We let the model explore or take random decisions initially during training before it starts exploiting the learned policy. The agent is trained for 62,000, approximately 62,000 epochs. And for a rough introduction of double DQ learning, what we do is we update the current Q value of a state and an action pair by taking the previous value and scalably adding the reward plus the maximum value from the next possible states. So for double DQ learning, this is where we use a different network. We compare our method against 2 datasets. One called Vedai dataset, which is an aerial images, vehicle detection aerial images, and Pascal VOC, which is a traditional dataset used in previous methods, and we use it for comparison purposes. Our method outperforms other reinforcement learning based methods and sequential classification methods in terms of IOU scores and computational efficiencies. As it can be seen here for Pascal VOC, RCNN has the highest IOU. However, the test time is much higher compared to our method. When it comes to aerial images, however, the story is different. Our method works much faster in terms of both training and testing, while also outputting higher IOU values. Do we really need history of actions in the state? Well, when we had done our ablation study, we found that adding 0 actions or not appending any actions actually improved the IOU. This was quite counterintuitive, but we realized that the states are self-sufficient to be Markovian and they do not require history information to be Markovian. We also ablated or tested against various terminal rewards. We found that always higher reward does not mean better learning. In fact, we found a sweet spot of over magnitude 3 for the method to learn much faster and better. Qualitatively, we can see that for Pascal VOC, our method zooms into the regions of where the aircrafts are. And for Veda dataset, we found that the agent performs well and can detect objects with good size ratios. Now, there are some limitations with this method. We found that the agent has more bias towards context. For example, it focuses on roads more often than farms. This can lead to misdetection of farm vehicles. Is it because the agent had more training data sets over roads and therefore it had more bias towards context? We believe that's the case. Thank you for listening to our presentation.
Good afternoon, everyone. Myself, Mohammad Aminur Hossain. I am from Space Application Center, ISRO. Today's my talk on the topics of reconstruction of missing multiband images for high resolution multispectral sensor using GANS. So this is my outline of the presentation. I'll talk about the introduction of our work, and then problem statement, what we have used for our deep learning based techniques, and then loss definition, and then visual and quantitative results on this. So high resolution multispectral sensor become an essential instrument in the rapidly changing field of the remote sensing. So for that advancement on the data processing techniques also enable new applications for mixed images such as mapping, agriculture, environmental monitoring, disaster management, etc. Development of such sensor become increasingly sophisticated due to the involvement of high spatial, spectral and temporal resolution. So such sensor designed using the complex optoelectro and then high data volume because of high resolution and the more than one bands there for multi-sector images transmitted through the ground station using the limited bandwidth. So images can suffer from the loss of one or more bands during this image acquisition data transmission. So it is immense interested in remote sensing community designed algorithm that would be required the data available from the available. So problem statement is the given images stack of n A bands with data loss and artifact in M bands or M greater than K. That is, if for a MX satellite image, A bands is given and the M bands number of M bands are missing. That N is greater than K. So then the task is to accurately reconstruct the missing bands from the available K bands. So this is a severely equals problem because this is a one to many type problem because the number of bands is available is less than the what we have to generate from the number of bands. So there are several methods proposed in literature with the normal images, the camera images, that is non-satellite images, such as image colorization, painting, etc. But some special technique generated using the some very less work is done in the field of high resolution on multispectral images. More recently, deep learning based methods shown very much superior performance using painting and synthesis as well as the colorization for satellite images. So some key baseline works including fix model and then GAN model and dense ResNet based model also used for single band generation. So our target is to reconstruct the multi-band images from the one or more available bands. This is a challenging problem compared to the single band images. Such as one is if single band is need to be generated from the 3 or more band, then more challenging from such a so network architecture. This is the normal network architecture for our model here.
Exploration of optimized semantic segmentation architectures for edge deployment workloads. Start with the motivation. So, semantic segmentation is basically about class-wise separation of each pixel within the page, and it has very widespread applications in remote sensing area, especially for anomaly detection, event detection, land use, change detection. Some common strategies for deployment in context of UAVs would be you can do this using cloud-based processing, where you would be sending the data to the cloud and then processing, and the network bandwidth would come. You would have the inference would be delayed. The other option is you can deploy it on drones which have compute capabilities, and that would allow you to get a rapid result. The only drawback is that you have to work with limited computational capacity, and you have to also take into account the power capacity. So for this example, for the study, the drone deployed data set has 7 classes building fundamentally. So the benchmark and it has 55 RGB with 10 centimeters. It also had elevation, but for the study, we only considered the RGB. The training and validation was divided into 85 and 50%. These are the architectures we explored in the study. So there were multiple segmentation models and also multiple feature extraction patterns covered in the study. In terms of segmentation models, we had included LinkNet, UNet++, ESPNet, SPN. And in terms of feature extraction backends, we used MobileNet V2, V3, ShuffleNet V2, ResNet V2, and EfficientNet V3. Our results of the exploration. That what we have had to characterize here are 3 points. One is the model size after the total operations blocks required for the and the IOU or the validation. Here I would like to highlight in terms of optimal performance, you see that UNet, SPN, and UNet++ show quite good performance above 0.5, almost 0.5. However, our focus is also to reduce the model size, for which MobileNet V3 offers a very choice. In case we are just focusing on the learning performance, then UNet++ with the IRNB provides the performance. The next thing that I want to focus on was since as we started the study from the drone perspective, so the main focus is to reduce the computation. For the study, we still making floating point we have in this case. So we explore TensorRT based implementations on FP32 and FP16, and you can see in this comparison that you don't observe performance degradation even switching over the resolutions. Precision. Another part that, and you see the validation line, this is the version on TensorRT in FP16. You can see all the different packets used with it. Next, we categorize inference latency on different platforms. For platform, GPU, which was a computer with the 2080 Ti, CPU was a Xeon server, CPU of the server itself. Then we used RPi and the Jetson lab. More or less, when using MobileNet, it would get optimal latency, but in case of if you want to characterize the study, we used resolution of line system across Fourier as certain was given and in the study by parameters, mainly the segmentation models, backends that we use for the extraction. And best it's a study that has a system. Optimization. The TensorFlow Lite was available, but when I was putting Geoscience, that's why I had to. I think the Geoscience Nano platform only had the model. And TensorFlow Lite also has an issue with segmentation. I tried the backbone. I tried the coding. Yes, I agree. Like find the right type of architecture, then you can further go on parameters. I mean, this is not something that I have done. Here I have tried to select the dimension. I couldn't really change the size. I start changing the sizes. That might I started. Obviously, we can change we can maintain it to a size. Loss function, we just use the dice. I tried the losses, but this trying to not run this exercise on it's not a survey, it's like a benchmarking. Not at this level, at this study. There are multiple equipment still.
Good evening, all. Myself Shanmukha Rao from NRSC or Indian Space Research Organization. Now I'm going to tell about my topic is remote sensing image restriping using deep convolutional neural networks. Here the problem statement is removing stripe noise from remote sensing images using deep convolutional network. And overview of the presentation is introduction about that stripe. What do you mean by stripe? And then stripe noise characterization for real-time satellite images, how the stripe is there, and then model architecture, and then training strategy, and after that results and conclusion. If we are seeing stripes, let us say if we are seeing that optical remote sensing images, which are if you are taking that push broom sensors, which are with the CCD array, so that because of inconsistent response between the CCDs, so we are getting the stripes. Here, they are the images of IRS1C data, which is at least 3 sensor of band 3. So here clearly we can see that here these are all the stripes are there. Because of inconsistent response of the CCDs. So for better utilization of the satellite data, removing the stripes is very essential for us, so that further applications, people, they can utilize the data effectively. If we see, let us suppose existing literature, if we are seeing that different categories of stripes are there, I mean, if we generally we can segregate these stripes into that 4 categories. First thing is statistical based methods, and then next thing is filtering based methods, and then optimization based methods, and then deep learning based. If you are taking that statistical based methods, so these are depending on the statistical distribution between the DN values of the image, they depend on that, so that there is a strong assumption that there is some reference distribution. Based on that only, these methods are working. Let us suppose if the stripes are not linear, so I mean, these methods will give that very poor restriping capability. Let us suppose if you are taking that filtering based methods, so these things will assume that stripe is a periodic noise. So I mean, one more thing is, let us suppose if the futures are which are having that same frequency as that of the noise, so that I mean, when we are suppressing that noise, the futures corresponding to I mean to the same frequency is also suppressed. So due to that one, blurring kind of effect will come. In the same way, some ripple kind of effect is also come. If you are taking the optimization based methods, so which are taking that latent property of the stripes, they are taking it, and then which are effectively removing. So if we see that many very good methods are there, but actually the main disadvantage is if you are seeing that which are very time complexity is very high. So because of that, I mean, let us suppose if you are taking IRS-1C, one image, we are taking almost per scene 50 minutes, we are taking that. In the same way, deep convolution network based methods, so many are there. So here we are focusing on that deep learning based methods, how it is performing for real stripe noise images. These are the metrics which I have used for quantitative as well as I mean, for quantitative analysis for artificially added stripe noise. I have taken that PSNR, peak signal to noise ratio, and then SSIM, structural similarity index, and then RMSE. So these are all for artificially added noise, because here reference is also there in the same way as well as de-striped image is also there. So I mean, when it coming to the real stripe noise images, so getting the reference image is not is not possible. So because of that one, we have to go with I mean, I have taken here normalized improved factor and then normalized distortion factor. These two are the indices which I have used. So these are all non-reference indices. So here first we have to train our model. So we want some noise image as well as the ground truth image. If you are taking that, let us suppose, I mean, here we have done that noise categorization. So how the stripes are there. So depending on that one, I have taken the clean image, and then I have artificially added the noise, and then I have given it as a label. So if we see that here, let us suppose if I am taking the vertical gradient, so which is not there. If we're taking that horizontal gradient, so stripe lines, I am able to see that. So because of that one, the stripe noise are there in along track direction. So in the same way, if I'm seeing the distribution, so which is having almost zero mean, which is having I mean standard deviation from 0.2 almost 1.7 to something. Here I have taken that 1998, I'm fully a different scenes of data, and then by using that, I mean I have taken that noise categorization. So here when I'm generating that labels image, what I have done is clean image I have taken, and then I have added the noise by taking that mean value is 0, and then with 0 to 5 standard deviation I have added, and then I have generated the labels. This is my model architecture, so which is already stripe noise removal wavelet based deep neural network. Here, which is having the 9 layers. First 8 layers, which is with convolution layers, and then along with ReLU activation function, and then 9th layer is which is only convolution only. So here convolution layers are 3 by 3, and then filter numbers are 64. And then here I have used the 0 padding to maintain the same input size, and then Atom is the optimizer. So here what I have done is, first I have taken that input image that I have transformed into that wavelet domain, so that we are getting that 4 coefficients like approximation as well as horizontal, and then vertical, and then diagonal coefficients. So my model is trained on the trained in the wavelet domain. So once that model was trained, and then I'm getting that I mean wavelet domain coefficients, then I'm applying that inverse wavelet transform, so that final output is coming. So this is the last function which I have used. This is that directional wavelet loss function, which is the mean square of each and every coefficient. So when I'm going for approximation coefficients, this is that this is the mean square error of that one. And then I have added some regular parameter also. I mean for that convergence. So which is that here LD is the regulation parameter, which I have taken that approximation along this one, and then horizontal coefficient this one. So here lambda value taken, which is 0.5, I have taken that. And then this is the training, training strategy. What I have taken is almost 48,000 images I have taken, which is around 500 by 500. And then 80% for training, and then 20% for validation. And number of epochs, 50 I have taken. Once the model was trained, I have taken 20 real stripe images. So the model was tested on that. So if we see here, our training almost, let us suppose after 40 epochs, which is almost stabilized. So I have run up to 50 and then I stopped that model. So here coming to that model performance, how I have evaluated. First, I have taken that artificial added image. So on that one, I have calculated the water metrics previously we have discussed. And then after that, selected that real stripe noise. So here our my model, which was compared with the two well-known optimization-based methods. One thing is LRS-ID, which is a low-rank single image decomposition. This is the optimization-based method. Here we are taking that rank of the stripe noise, which is very low, and then a non-convex L0 model. So by using these two methods, I have compared the model performance. If you see here, for added stripe noise, we see first column. Left one is the ground truth image, and after that, this one I have added the here I have added the noise here. Clearly, we can see that, and after that, this is by using that LRS-ID method, and then this is by using that L0 convex method, and then this is the SNR-WDN. What our model we are discussing, that is this is the output of this one. So here we can see that here little bit smoothing was happened when it come to that LRS-ID. So these two methods are almost similarly which are performing. So these are all the indices. If we see the metrics. So this one LRS-ID for sparse model, and then SNR-WDN. Here we can see that SSM. If we see that SNR-WDN, which is performing better, 0.99, and then SNR also, PSNR also, RMSE also. So these are all the values. So this is for added stripe noise image. And then these are all the real-time stripe noise images. So which one I have taken from IRS-1C data, and then applying this one. So here clearly we can see that some features which we are smoothing, and these two if we see that almost in similar way. So this is one more image. So clearly you can see that here these stripes are effectively removed. This is the 12th May 1998 data. And then here also we can see that here by using this method, which one here this line futures we misread. And then here clearly we can see that this one this bridge is there, which was because of the smoothness it was this one. But when coming to that, these two methods which are performing in almost in a visually which are almost similar. But coming to that index metrics, here NIF and NDF we are taking. NDF actually indicates that the distortion in the underlying image. NDF reaches to 1 is the best optimum value. That means there is no if it is approximate to 1 means there is no unwanted noise which was unwanted information was not removed from that one. And NIF which is close to 0 is better. In the same way, it should be in positive side. If it is more negative side, there is a collateral degradation between that. And when if it is towards that positive side, then we can the image is more getting smoothness. So here we can see that almost these two are in similar way they are performing. So coming to conclusion, here SNR-WDN and the non-convex L0 model both are superior as compared with this one, and SNR-WDN which is equally comparable with that, and both models are removing stripe effectively without removing without doing that smoothing and all. And then coming to SNR-WDN, the TAT is very less, almost within 10 times improvement was there, because here what we have done is we have taken that list 3 image 6K by 6K, and then 500 by 500 chips we are dividing, and then again we are merging it. So within 1 minute only we are able to do that destriping. Whereas here non-convex L0 model which taking more time. So coming to time point of view, which is very advantage with this one, with this model. And then coming to the production environment, which is within a short period of time we are able to generate the product. So here, by using this method, which is benefited, so that we are planning to make it operational in our IMGS chain, in the data product generation chain. And then when we near future, we are trying that by using this SNR-WDN model, we are trying to explore for oblique stripes. I mean, this is only for vertical stripes only, which is in that radiometrical space. I mean, when it is coming to that oblique stripes, we have to see that. Okay, thank you. These are all references. Thank you. Sorry. The conversation neural network. Sorry. Yes, sir, I will. Yes, sir. Yes, sir. Yes, sir. Yes, sir. Yes, sir. We are using. Actually, no, sir. By using radiometric lookup table, actually conventional thing is there. Actually, if you are calibrating in a better way, so it won't come. But actually, at that time, that calibration something is there. So when our stripes are coming, we are using that, sir. At present, in regular chain, we are using optimization based method. At present, regular chain. So now we are planning to replace with this one. No, sir. No, sir. Present thing, no, sir, they're correcting, but actually this is the old data. So we are doing that reprocessing that, sir, with the existing technology. This is almost, I mean, 1998 data. Yes, sir. I said freely available. I mean, yes, sir. Just the list 3, sir, which is freely available. Now what we are doing is, we are planning to do all data reprocessing, sir. At present, all data we have to do reprocessing and keep it in storage. So whenever user is asking, no, no, no. So coming to the temporal evolution, sir, some people are still there asking. So, so for that point of view, we are I mean, with the latest available. Let us say at that time, sir, let us say geometry wise also, which is I mean very less accurate. In the same way, radiometry wise also. So with the currenting trends, we are doing and then keeping it. So people will ask, they will do it. In the same way, at our application people also. So for temporal, I mean time series analysis and all, they are very much interested by using this data. So that's why we are doing it reprocessing. Sir, actually, coming to real stripe noise images, sir, we have characterized that, okay, deep learning model is also working fine. Let us suppose if we see most of the papers and all, I mean, for added stripe noise, how it is behaving, that we are doing it. And then coming to that real-time satellite images, we can demonstrate that by using this, we can, I mean, in production environment, we can keep it. Sir? I mean, best we have tried. I mean, for other things also we will see. And we will try, sir. But at present, as a part of operational point of view, we have explored these models. I mean, for other things also we will. Ma'am, actually, I mean, when it is coming to that LRS arena, ma'am, which is getting that smoothness is happening, ma'am. Because of that one, let us suppose if I am taking that SSIM, what it will measure that structural similarity. So when there is a sharp features are there, so which is smooth. Yes, ma'am. Okay, ma'am. More or less are equal. Yes, ma'am. Actually, no, ma'am. More or less, I mean, whatever indices are there, I mean, visually and then quantitatively both we have to see. That will at present I don't have that. Sorry. How can? Actually, by using that LUT-based radiometric LUT-based correction, we have to do it. Actually, in lab-based, actually they used to do that characterization. Let us suppose our CCDs are there. We are eliminating into the I mean integrated sphere, and then we are getting that. I mean how the response is coming that. So by using those things, they used to generate some LUT-based kind of thing. Let us suppose for a particular this particular input, what is the gain and then what is the bias they used to calculate. So actually that is a standard procedure. Even then still, let us suppose even after launching also, I mean depending upon the aging of the detectors also, it used to introduce. So at that time periodically calibration used to be happen. But actually for this satellite still there is an issue. So those things by using these methods we can address that. I mean, by accessing training data, obviously.
Good evening, everyone. So I am Hitesh Jain, final year undergraduate from IIT Gandhinagar. Today, I will be presenting on this topic of investigating large vision model training challenges on satellite dataset. So talking about introduction, so there are different remote sensing applications like environmental monitoring, urban planning, disaster impact, and there are some large datasets that are openly available like SpaceNet, QFabric, which have shown robust performance on training models. But there are also some nuanced task-specific data set, such as C-Drone, CV2, XView, Mafat, which are being shown here. The performance haven't been really good enough on training because of their small size. So we can explore the use of zero-shot capabilities to enhance the versatility of the data set by or by downstreaming tasks. So talking about the motivation, so a recent paper says like on how when foundation models have seen satellite images, it shows like how like the zero shot performance of Eurosat and BGATNet S2 dataset on CNIP model, and the performance have been pretty low. So satellite images are not like have not been when training foundation models. So there are various differences between satellite images and conventional images. In terms of orientation, conventional images are taken in the front view, whereas remote sensing images are taken from top side. Conventional images are generally consist of 3 bands RGB, whereas remote sensing images can consist of multiple bands. Conventional images are generally uniform in size, whereas remote sensing images can be as large as possible, and they differ a lot in size. So this led us to a pivotal question like, can foundation models be trained out of box for geospatial data? So I'm talking not about CNIP. So what exactly it is? So CNIP stands for Contrastive Language Pre-training. It is trained over a big data set. It is a diverse data set containing around 400 million image text pair. It has been drawn from the internet. It shows exceptional zero-shot capabilities and outperforms fully supervised baselines. So talking about CNIP model, when pre-training, we have a stack of images and stack of neighbors. The images pass through the image encoder and the captions pass through the text encoder, and we get a vector of text for each captions and a vector for each image. And then we form a matrix. Our main aim here is to maximize the diagonal elements as much as possible, such that the first image is highly coordinated with first caption, second is highly coordinated with second caption, and so on. So talking about the dataset development, we have chosen dataset from different remote sensing context, problem type, sensor, resolution, image size, and channels. So these are the datasets that we have used: Agriculture 2017, BGATNet S2, S1, C-Drone CV2, XView, QFabric, Hossain Nova, and Mafat. So the image size is varying a lot. So to make it uniform, we used patchification techniques to like take 512 cross 512 patches from each images, and we created a dataset of around 4.5 million image text pairs. This dataset was stored in the web dataset format, which is well known for its distributed training purposes. For the validation set, we have taken around 1% of the whole dataset, and we have carefully curated it such that there are no overlapping samples, and the validation process can be seen clearly. So talking about the experiment, we conducted the first experiment on the combined dataset. We used the open source implementation of CNIP model by MN Foundations, and we see no significant improvement over 18 epochs. And these are the results that we got. Here we have used 3 metrics: R1, R5, and R10. So these are the recon metrics, and this tell us about like what is the like when we start with the validation process, we get a probability for each of the neighbors, and R1 takes the top one neighbor, R5 top 5 and R10 top 10. So what our hypothesis, like because of the no graded performance, was like resolution might significantly affect the modern performance. So to see like whether our hypothesis was right or not, we grouped the dataset in 3 different categories based on resolution. Bgartner S2 was about 100,000 centimeter in resolution. Agriculture 2017, Drone CV2, XView, QFabric, Hossain and Mafat. So we grouped them into 3 different categories, and individual training experiments were conducted. So individual training experiment was conducted on a Bgartner S2 dataset, and we see a significant improvement in the performance. These are the graph, and we have Fawn's prediction and true prediction showing the correct samples are marked by green, the missed one are marked by blue, and the red, the Fawn's one are marked by red. We perform the training until the NOS converges. So experiment 2.2, we trained KNIP on the next set of data set, Agriculture 2017 and Seed Drone CV2. We see again a improvement compared to prior results. And here are the fonts in true prediction. Next, we trained KNIP on the mixed resolution dataset, having resolution ranging from 30 to 50 centimeter. And we see a lot of spikes here. It's maybe because of non-uniform resolution. And these are one of the fonts and true prediction. So we thought of incorporating resolution and satellite information into the text encoder of the KNIP training. So we passed on the satellite information and resolution along with the labels and retrained the KNIP. The red one shows here is for with satellite information, and the blue one is without satellite information. And we see a significant improvement in R5 and R10 compared to the prior results. Whereas there was a decrease in performance of R1. This might be due to the varied outcomes that we received. Talking about conclusion, what we conclude is like resolution variation is a key determinant for KNIP performance. Integrating satellite information into the text encoder enhances modern interpretive capabilities. To further enhance the performance, what we are trying to do is we will augment the labels using an open source large language model, and such that it generates a caption that will consider the interaction between different labels, satellite information, resolution, and we will retrain the KNIP model again for the news data set. These are the references. So the core application is foundation models are well known enough for their performance, zero shot performance. But there haven't been any modern in the geospatial context, because geospatial context is very much different from the conventional images. So we are trying to train a model, foundation model for geospatial. So we can use foundational models to enhance the versatility of the data set. Like some data sets are very much small, so we can increase the sizes. Also, once the data, the foundation model is ready, we can use it for the downstreaming task. We don't need to perform training again and again. Yeah. So the image encoder here, it's either ResNet or Vision Trend. X-axis is the data set we have trained on. the validation set, like that, like 3.1K samples have been trained. Yeah. So there have been lot of oscillations, so the training is not going properly. Also, we notice like after 18 epochs, the NOS suddenly becomes NAN. So we need, because of like we should resolution differences that we have seen. It might be because of the INGARSS, like the learning rate that we have used. Also because of the resolution differences that are there in the different data sets.
Hello,
We will now start paper 59. Are you online? Can you just confirm?
oh yeah, you can
Yeah, okay. Thank you.
everyone. My name is Xin Zhao, come from Shannon University of Science and Technology. The title of my report is Hyperspectral Remote Sensing Reflectance Data Augmentation Method for Red-Tined Dominated Species based on condition generative adversarial net. My collaborators include associate researcher Rongjie and researcher Ima from the Foster Institute of Oceanography, Ministry of Natural Resources. My presentation will focus on the following 5 aspects. First, red tide is a marine disaster that results in water discoloration. The red tide outbreak leads to marine life status, posing threat to ecological balance and human health. Marine phytoplankton are the primary organisms responsible for causing red tide. Among the more than 4,000 species, over 260 can cause the red tide, and the 70 can produce toxin. Therefore, accurately identifying the dominant species is essential for determining the toxicity of red tide. Different dominant species have different absorption characteristics, such as the absorption peak position, reflection peak position, and absorption peak. The common method also needs a lot of reference spectra. However, the in-field hyperspectral remote sensing reflectance spectrum collecting at the red tide site is difficult and available samples are limited. So, research on spectral data augmentation techniques is crucial for dominant space identification in red tide. In our study, we use 3 red tide dominant species. The in-field remote sensing reflectance spectrum are measured by ASD. A total of 40 set of in-field normalized hyperspectral remote sensing reflectance spectra are used in our study. Based on this, further processing was conducted on the remote sensing reflectance data of dominant species of red tide. It includes 3 steps. Firstly, the original remote sensing reflectance spectrum was subjected to Lawyer's filtering to minimum random noise. Second, the second derivative of remote sensing reflectance was calculated to enhance the spectral differences between different species. Third, to emphasize the differences in spectral shifts between different dominant species rather than their values. The derivative spectrum was normalized. Therefore, the normalized second derivative remote sensing reflectance spectra were used to study the data augmentation method. Moreover, the Poisson correlation coefficient and the spectral angle as the evolution matrix to evaluate the effectiveness of the data augmentation. The important our study addresses the challenge of acquiring high spectral reflectance data for data dominant species of red tide by proposing a data augmentation model based on conditional generative adversarial networks as a CGAN. We incorporate the characteristics of high spectral reflectance data and employ the linear layers as the fundamental layer of the network. This model consists of a generative network and a discriminant network. The objective of the generator network is to learn the distribution of real samples and generative synthetic samples that resemble real samples. Therefore, the generative in this model compares 5 linear layers, and the discriminator has 4 linear layers. Also, the leaky IELU activation function is primarily used. For loss function, we select the RMSE. In training, our input was the normalized spectrum. Our output was the second derived spectrum. The model training parameters also include 5,000 interactions, and the batch size is 8. To assess the correlation and the spectral similarity between the model result and the reference data, 600, 800, and 1,000 sets of augmentation data were randomly selected. The result indicates that the augmented spectrum exhibit good consistency with the reference, with an average correlation coefficient of the percent of 98, and an average spectral angle of 3.82 degrees. The number of augmentation data has little effect on the augmentation effect, indicating that the model has strong stability. Considering the experimental time and the spectral similarity, we select the 800 set of augmented data. The picture on the right is the second derivative result of 800 set of augmented data and standard. The top is standard and the bottom is the augmented. For this result, we can find that the different species have the different significant differences in spectral shapes, while the difference within the same species are relatively small. This indicates that the data augmentation method can better emphasize the difference between different dominant species of red tide, and is expected to provide more effective spectral data for ID identifying dominant space of red tide. On the basis of data augmentation, the dominant species recognition experiment was conducted using the SVM trained with 800 set of the augmented data. We use the 14 set of reference spectra to test the classability of augmented data. 3 dominant species recognition accuracy was the percent of 92.5. The model performed the best in identifying the red tide species, while there were misclassification for class 1 and class 3. This mainly because of that the 2 species are both belong to diatoms, and their reference spectra show less difference compared to the other red tide species. Finally, make a conclusion. In this study, we develop a high spectral remote sensing reflectance enhancement model for red tide species. This model based on 3 types of measured data using CGAN. Also, this method yield augmented red tide species data with a good consistency with reference spectrum. Not only that, the augmented data enable successfully used in dominant species recognition experiment. Consequently, this method effectively enhanced the high spectral remote sensing reflectance data for dominant species of red tide, providing rich and reliable data for building red tide dominant species identification models. My report is over. Thanks, everyone.
Okay, then we'll close the session.
Yeah, it's the parameters is adjusted through training. It's the best for this this parameter. Do you have it here?
Yeah, you were audible. Thank you.
Yeah.
Thank you for your presentation. We'll now close the session. Thanks to Dr. Shamlal and Dr. Silpa Suresh for chairing the sessions, and that'll be the session. Thank you.